Section 12.6, we're going to talk about parametric surfaces. So, in Chapter 12, which is the chapter we're on, we've emphasized the connection between a vector-valued function and parametric equations. In this section, we will extend the idea of parametric equations to those with two independent variables. So far, all of our parametric equations have either used, for the most part, t or theta, right? Kind of depending on whether or not we were working with a curved surface. We used thetas a lot with sines and cosines, of course, and t was used a lot because we're talking about time, those kinds of things. This section, we're going to actually look at taking two variables and using a parametric equation to draw graphs and to go back and forth at least a little bit with parametric versus rectangular coordinate system. Does everybody have this? Are we close? Yeah? Okay. All right, so we're going to do an example, two examples actually, of sketching first. So we're going to sketch the graph of the parametric surface. By hand. As we do this, well, let me write this down and then I'll talk. So x equals u, y equals v, and we're going to have z equal to u squared plus 2v squared. So here's our parametric equation. And you need to remember back to the section that you guys didn't like very much in Chapter 11, which was on sketching as well. And so some of those pieces of information, those equations and stuff, are going to come back again. So in particular, as we take a look at this one, you might notice that x is u and y is v, which doesn't really look like it's very in-depth. Right? This is not a very exciting situation. But we can use that information to change this into a rectangular equation very quickly. So the z value, for instance, can be written as u squared, so that's x squared, plus 2v squared, which is 2y squared. So there's our rectangular equation, which we have worked with before. And from 11.6, that was the section we did, we know what this is. Do you remember? Nope. What would it have to be? Let me pause there for just a second. What would it have to look like to be an ellipse? There's one change that would need to be made. The what? No. If it were equal to 1, like if the z here said equal 1, we'd actually have a cylinder. An elliptic cylinder. What's that? Negatives give us hyperboloids. Yeah, we need a z squared in order to give us like an ellipsoid, which is what you're actually thinking, like a three-dimensional ellipse, like a football shape sort of. Yeah, we need a z squared. So this isn't that. We've hit on everything it's not. This is a paraboloid. So if you take a look at this, this is, if you ignore either the x or the y, I don't care which one you want to ignore for a moment, you would have z equals the square of the other one, right? Which would give you a parabola shape. So if we ignored one of those squared variables on the right-hand side, you would get a parabola. So you're getting a parabola around the z-axis, both in respect to the x value and in respect to the y value. So in terms of your graph, this would look something like, oops. Can you see a three-dimensional shape there that looks sort of like a bowl? Are you good with that? It's about as good as my sketches get. So it should look like a parabola, both around the x-axis and around the, up around the z-axis, both with respect to x and respect to y. So what we're going to be doing is just this, changing this into a rectangular equation, and then remembering or referring back to section 11.6 if you need to. There is a review posted out online for this material for chapter 12. If you want to go print that out later to do in class on Friday, we'll start with that. And you do have the ability to use a 3x5 note card again. So if you need some of those pieces of information from 11.6 for these graphs, that might be a good use of part of that space. All right. We're going to do another one. Same directions, so I'm not going to rewrite those. My equation, I'm going to give it to you in the format for R. So R equals U cosine of V I plus U sine of V J plus U squared K. On purpose, I wanted to start with something that was very straightforward, very simple. It was really clean. We just replaced the x and the y, no big deal. Here, we could actually write these as the components x, y, and z if that helps you to see it better. But very quickly, you should see that this is more complicated than the last one we dealt with, because each of the x and the y, anyway, both are in terms of u and v. You guys see that? So that's a little bit messy. I mean, we don't have the ability to just solve one of them for x and substitute in the other one. And in particular, while we could try to solve one of these for u and substitute in the other one, it's messy because I've got signs in there. So I certainly wouldn't want to solve for v, but even if I solved for u, I would end up with something that's messy looking. And anytime we have sines and cosines, it's often nice not to solve for something anyway, because the Pythagorean relationship. So where I'm going to start on this one is I'm actually going to start with taking a look at what happens when I square x squared plus y squared. Because if I end up with a sine squared plus cosine squared involved in that, that goes away, and that's a very nice feature. So that's where I'm going to start on this. I've actually got u cosine of v squared plus u sine of v squared. And then if I square each of those components, I get u squared cosine squared v plus u squared sine squared v. And then what? Yeah, this is just u squared. And the reason is because I can factor the u squared out, and then I have the cosine squared plus the sine squared. So x squared plus y squared is actually just equal to u squared, right? Okay, but I could have done, and I didn't write it to begin with because I wanted it to not be as sort of confusing as to why I was doing it. I really want something with x's and u's and y's and v's in there. Whoops, let me write it this way. So I know from my equation up here that the z is actually equal to u squared, right? So instead of leaving that as u squared on the right-hand side, we can write that that's z. So I've got a rectangular equation that looks an awful lot like the last example I did, but it started out a lot different, all right? So the parametric equations were quite different to start with, but the answer ends up being very similar. Not the same, but very similar. What is this a shape of? Paraboloid, just like the last one. No, it's not a trick question. I tried to decide whether to do a different one, and I decided I wanted to do the same thing because I wanted you to see that really you can't look at where you started and know for sure where you're ending up. That these started out very different, and they actually ended up in pretty much the same place. Now, it's not exactly the same paraboloid, right? But it's very similar. The only difference is that I don't have a 2 in front of the y, right? So this is a paraboloid. It's still opening around the z-axis. Agreed? Because that's my value that it is not squared. So we'll try and draw the same kind of graph I did before. Yeah, so you guys didn't get the joy of watching me try and graph in 3D before, huh? Was Dr. Nichols good at graphing in 3D?
He just made us.
He didn't even have to do it for you, huh? Yes, Jordan.
So is this one going to be too good for Avalon, just like spin it around?
Yeah, it's now if you want to talk about the difference between these two, obviously my pictures don't look any different. They're just sketches. But there is a difference, obviously, between them, right? Like on the other one, I had that 2 in front of the y, which means that in the y direction, I've got it more elongated, or I'm sorry, steeper, rather. And so in the x direction, it looks sort of more flattened out, kind of like a parabola would do. This one would actually be the same image. This would actually be much more like a traditional bowl-shaped if you actually had it, you know, coming down more to a point at the bottom instead of a flat surface on the bottom to actually be able to sit on the counter. But this one would be more symmetric. It would be symmetric, in fact. Yeah. All right. In many cases, the parametric equations are determined by the geometry of the object. Some curves, for example circles, or shapes that have a circular cross-section, are more easily described in polar coordinates. And let me just give you an example of that. So in rectangular coordinates, if we had the equation of a circle, we describe that as something like, and this is just in 2 dimensions, x squared plus y squared equals some value that's r squared, some constant r, right? But if you were working in polar coordinates, this would actually just look like r equals some number, because you would just be looking at the radius of the circles, you know, and so forth. So it ends up being a much simpler equation with no squares, and it's nice and pretty and clean to do this with circles. So what we're going to do is we're going to go the other direction. That is, we're going to start with a rectangular equation, and we're going to write it into parametric form, which we've done before, but we're going to do this with a little bit different equations than we did before. So we're going to find a parametric representation of the surface. And the first one that we're going to start with is z equals 3x plus 4y. All right, so taking a look at this, it didn't say the parametric representation, right? It says a parametric representation, because just like you saw in the last 2 examples, they were nearly the same thing, but they didn't start out looking anything alike in parametric form, right? So there's often more than one answer. In fact, there's always more than one answer. There may be a simplest one, But there's always more than one possibility, which makes grading super fun because I have to figure out if yours is going to work. So let me give you a very simple one on this one. And this sort of looks like what we did on example number 1, but of course backwards. So we need to define what in the world is x going to be, what is y going to be, and what is z going to be. The easiest and yet not very helpful definition is that we can let the x be u and the y be v, just like example 1 gave us, and then z would be 3u plus 4v. I mean, that's the simplest thing we could possibly do here. Could we get more complicated and more fun? Of course. You could let you could let the x and the y be a lot of different things. It's just going to affect then what z is going to be when you work through that. Okay? So we found 1, which is all we're asked to find, so we're going to stop on this one. But there's lots of other answers that you could choose and could work with on this to make a different parametric system or parametric equation for this rectangular equation. All right, we're going to do another one, a little bit more involved. Not a lot, but just a little. The question makes it sound much more complicated. This is the portion of the graph x squared plus y squared equals 4, which is a what? It's a circle. Okay, good. We're going to do this portion from z equals 0 to z equals 2. Now, in 2 dimensions, this is a circle. What is this in 3 dimensions? No. A cylinder. Because I don't have a z in the equation, right? Which means z can be anything. So I've got basically like circles stacked up on top of each other. That's really what I have. If you remember doing things with discs and washers in Calc 2, imagine having a bunch of discs or washers just stacked up on top of each other, right? So it looks like a cylinder. Now, our cylinder is only going from a height 0 to a height 2. So it's got a definite height. So it really does look like the toilet paper roll or the paper towel roll, okay, something like that, or a can, because it really stops. It doesn't go infinitely up and infinitely down. So we have that going on as well. But we mentioned back over here, and this is why I mentioned it, although I guess it's a little bit out of order, that there is a much more natural approach than simply letting x be u and y be v like we just did a moment ago. It's much easier to work with this with thetas and r's, right, in polar coordinates. So that's what we're going to do on this one. We're going to let our x value, in essence, be r cosine theta, but you know what r is, so we're not really going to use r. What is r? It's 2. How do you know? Yeah, because this 4 right here is the radius, or at least it determines the radius. Its square root is the radius. So if x is 2 cosine theta, what would y be? 2 sine theta. Exactly. And again, this isn't the only way. It's just a very natural way to do this based on what we've done so far. And then what is z going to be? You can call it whatever you'd like. The variable that we've used before has been t, but there's nothing special about t, so use a u. You could use an r if you want. I probably wouldn't use r just because we have this sort of an association with that being radius. But it's some other variable, right? Some other parametric piece that's going to be changing. But there's some conditions on this, because if I do this, just written here like this, I'm going to get that infinite sphere, cylinder that's going up and down forever, and I don't want it to do that. I need it to stop. It needs to start and stop between 0 and 2, right? 0 and 2 on what? I mean, like, I need conditions on theta and on t in order to make this work. We'll start with t because that's the one I was just talking about. What are the conditions that have to be present on t to make this not go up and down forever? Yeah, it has to go from 0 to 2 just like z did, because z and t are the same quantity, right? Defined differently, the same quantity. Why do I need to do something about theta? Any idea? Yeah, we don't want it to keep spinning. It only needs to go around one time to get this image, yeah? So what are my limits going to be on, or my upper and lower bounds, if you will, on theta going to be, or could they be? 0 and 2 pi works as well as anything else. I mean, it works better than a lot of things too, but it's a very natural approach to do 0 to 2 pi, right? We only need it to go around one time. What's that? Say again for a camera.
You just want to go around like one circle, right? Like 0 to 10 or just any.
You want it to go around one time. We don't want it to spin for, yeah, we just need it to go around one time. So we're going to, if you didn't want to use 0 to 2 pi and you wanted to be more creative, maybe you decide you wanted to go from, negative pi to pi. That would work too.
So you want a period of 2 pi?
Yeah, we want a period of 2 pi,
Okay,
exactly.
that's what I was asking.
Yes, that's correct. All right. This is all we're going to do in this section is these two ideas, okay? So I'm going to give you the homework set now. This is page 802. 2, 4, and 5, those are going to be ones we're going to sketch. So there's just 3 for sketching. And then 18, 20, 22, and 24 are going to be parameterizing.
Can you pick this one up and not 12.5?
We'll see.
I don't feel like this